Vậy và tomorrow học lý nha em. Biết mai học lý không? Mai học lý.
Okay, please sit down. We are going to start. Okay, are you ready? No? Please come on, come on. Okay, please sit down quickly. Please, can you close the door? Okay, so quiet, please, quiet. Okay, so we were in the chapter 23 of which is about Gauss law. Okay, so the Gauss law, as here I express here, it relates the charge inside a closed surface, okay, to the net flux of the electric field through this surface. Okay, this is the Gauss law, and we have started to apply it here for different systems, for different geometry, and yesterday we ended with the case of an infinite line of charge. You remember yesterday? Okay, so today we are going to do the same thing, just to be sure that you have understood. About now, we are going to calculate the electric field created by a plane of charge. Okay, so sorry. So electric field created by by an infinite plane of charge. Okay, and I'm going to specify that it is an insulator. Okay, so here is so we have a vertical plane, okay, and this is an insulator, and we have some charge here. Okay, but this charge could be like this. Okay, they are fixed. And the question again is, what is the electric field at the point M, which is, let's say, distance of, let's say, distance Z, okay? Do you understand the question? Yeah? Okay, great. I'll let you 1 minute to solve the problem. Okay, so who can tell me how are we going to solve the problem quickly? Come on.
Can you say a question again?
Sorry?
Can you repeat the question?
I would like to know someone who can tell me how to solve the question. What is the electric field at point M? Come on, come on. Okay, so I'm going to help you. So by symmetry, you can understand that the point, let's say, M prime here, by symmetry, has the same electric field at the point M. Are you agree with that? If the distance to the plane is the same? Yeah? Yes or no? Yes, of course. So, what we are going to do to solve this, remember that we are in the Gauss law chapter, okay? So, we are going to consider a small cylinder going through the plane, like this, okay? And which section is going through M and N prime, okay? This is a cylinder surface, closed, of course. Okay? Do you see what I mean? Okay, so according to you, how is oriented the electric field? How is oriented the electric field? Okay, so of course, because the plane is infinite, necessarily the electric field is oriented in that way. Okay? And in the opposite way, of course, it is like this. Okay? So now we are going to apply the Gauss law, so according to the Gauss law, the net charge, okay, so of course this is the section here, and of course I didn't mention it, but the plane is characterized by the surface charge density sigma. So, could you write the Gauss law in that case? So, the flux across the closed surface is equal to Q inside the surface. Okay, we also call the net charge, but it's just a name. Okay, so this again is the flux of through the surface lateral. This is okay, plus the flux through S1, for example S1 is here, plus the flux through S2, S2 is here, okay, and is equal to, so what is the Q inside? Okay? Do you follow me? Yes?
You a little slow down.
Slow down, okay. So again, the flux of the electric field through the closed surface that I have defined before, previously, okay, is the sum of the flux through the lateral surface of the cylinder, okay, I call it SL, plus the flux through S1, plus the flux through S2, and according to the Gauss law, it is equal to the charge inside. It's okay now? Okay, so, according to you, what is the first term? 0, yes, because all the electric field are perpendicular to the plane. So all the electric field are parallel to this surface. You understand?
Yes.
Okay, so this one is 0 plus. What is the second term? What is the second term? So, because here the small vector dA is outward, remember that the dI or the dA vector have to be outward, so dA is like this. Okay, so in that case the dot product is positive and it's equal to E times S1, okay? Oh, sorry. This is the second term. The third term is the same because EM is like this and GA also is like this. So here we have also EM prime S2. Okay? And this is Q inside. Okay, so now what is it? S1 equal S2 equal, let's say, nothing. S. Okay? Okay, so now we have 2 epsilon 0 because em equal em prime S1 or S equal, what is it? The charge inside the cylinder. So it's the charge which is here now in this surface. Okay, so this is sigma S. Yes? Okay, so at the end you can write that the electric field is equal to sigma over 2 epsilon 0. And that's it. It is okay? Is that clear? Any question? Okay, another example. Slightly different. So now, sorry, I'm going to move to, so until now, I have implicitly assumed that all the charged objects that we have studied together are insulator. Okay? Meaning that the charge inside these objects are fixed. Okay? So now I would like to consider a little bit the case of conductor. Okay, so let's move. Okay, so this is chapter part 23 times 25. So electric field created by the charge conductor. Okay, so the difference, okay, so just to make, in a conductor, charge are free to move. Okay, so if we consider here an insulator, okay, and imagine that I can put in this is an object, some charge in it. So these charges are fixed. Okay? But now, if I consider this the same object, but in metal, for example. Okay? So here, what happened? The charge which are positive, for example, they are all of the same sign. Are you okay? Okay. So what will happen to the charge here if they are free to move? Okay, because the charge are all the same signs, they will have the tendency to repulse each other. Okay. And how can they repulse each other? They will go to the surface, because this is the best way to optimize the distance between each charge. Do you understand this? Yes? Okay, so in charge, in conductors, we charge, of course. Charge have the tendency to be located on the outer surface of the material, of the object. Okay? So let's consider another example. So let's say, for example, this one, but with a cavity. Imagine that there is a cavity. Okay. So if I put charge here, okay, so because the charge again have the same charge, they have the tendency to be repulsed each other, okay, and so they are going to move to the outer surface. Because this is the best way to optimize the distances between the charge. Okay, so we will have this. Okay, all the charge we have the tendency to move. You understand? Okay? So this is an important property of conductors. Okay? So now, yes. So of course, just one remark, important remark. Inside here, for example, M. Let's consider a point M inside the conductor. What is, at the equilibrium, what is the electric field inside? So, according to you, what is the electric field inside it at this point, for example? But is 0. Why? Because if there is an electric field inside, then the charge will move according to the electric field. There will be a force acting on the charge, right? And so the charge will continuously move inside the conductor. And at the equilibrium, of course, it is not the case. You understand what I mean? Yes? So inside is 0. Okay? So here, EM equals 0. Okay, so now what is, the next question is, what is the electric field just at the outside the conductor? Okay? Okay, so we want now, for example, to calculate, let's say, N, the electric field outside. Okay, so of course, this will depend a little bit on the shape of the object. But if we make a zoom here, we still can consider that locally the surface of the conductor is almost flat, okay? And that's why I said just outside, meaning very close to the surface, okay? Okay, so if we consider this, we have a lot of charge here. Okay. And we have the point N here. Are you okay? So now, how are we going to calculate the electric field at this point? We are going to apply again the Gauss law. So we are going to consider again a small cylinder here. Okay, this is okay, and we are going to apply to do exactly the same thing as previously, but now be careful, it's a conductor. So okay, so this is sigma again, the density of charge. This is S1, S, this is L, the length of the cylinder, okay? But now, what is different here is that the field here at the point N is like this, but here the field is 0 exactly. So here N prime, E of N prime, this is not right, equals 0. Okay? Okay, so now if we apply the Gauss law as before, so according to the Gauss law, epsilon 0, the flux of the electric field through the surface is equal to the charge inside. So here again, of course, locally, all the electric field are perpendicular to the surface, okay, as before. So the flux through the lateral surface of the cylinder is again 0. So at the end we have epsilon 0, E of n times S. This is, and the charge inside is like before, here, sigma S. Okay, so here the electric field just at the surface of the conductor but outside the conductor is epsilon 0 over sigma, and not, remember, not sigma over 2 epsilon 0 in the case of an insulator. Okay? Sorry? Sorry. Very good. Sorry. Sigma over epsilon 0. Thank you very much. Okay, so again, for a conductor, the electric field is sigma over epsilon 0 and not sigma over 2 epsilon 0 in case of the insulator. This is a difference. Okay? Okay, this is, what is it? Whatever. Is it okay? Can we continue? No? Okay. Okay, so now let's start a new chapter. The next chapter is about no, it's not finished. Any question for, yes, please? You mean the distance from here to here? Yes, here in that case it's not necessary to have something symmetric. You're right. Because you can take any, for the point n prime here, okay? You can take any point inside in the in the conductor, because the field at any point of this point is equal to 0, okay? It is in contrast with the previous one. In the previous one, we had to take a symmetric point because the field at these 2 points are symmetric. Okay? Did I answer the question? Here, it depends on the geometry, but yes, for a plant, they had to be equal. Sorry, are you afraid to not understand? Yes, please. Can you show me what you want to? No. 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 Yes. Yes. No. They are not. They have no specific distance, but if we take. Okay. The question is, if you have an object like this, okay, you have plenty of charge. Okay. You want to ask me if the distance between these charge are specific? No, we don't know. It depends on the charge. Okay, but we just know that the distance are the largest as possible. Okay. Okay. Thank you for your question. Okay, so let's move to the next chapter, which is chapter 24. So now I am going to present you the notion of electric potential. Okay? Okay, so now let's start by the first part. So now imagine a charge let's say Q, which is, let's say, going to a point E to a point G. Okay. And this charge is surrounded by an electric field, whatever. I'm sorry. Okay. So, E, this is E. And of course, this charge is submitted to the force, let's say, the electric force, Fe. You remember? Okay. What is the formula of the electric force? Do you remember? Yes, it's Q times E. Okay? Okay, so this is you had a mechanical course in the first semester, no? Yes. The last year, I did this course, so I know what you have done. But okay, so the work of the force on the path EG. Okay, do you remember what is it? The work of the force on the path EG is the integral of the force time, let's say ds. So ds are the small You remember this? The small displacement here. Okay, whatever. So, the thing is that you can understand easily. So, from where comes this force? Or in other words, this is an energy. Okay. So the question is, from which energy is coming this work? Okay, because the work is the energy, let's say, spent depends by the force. Okay, so question. So this is. So the work is the energy required to move the charge Q from I to J. Okay? Are you agree with that? So the question is from okay, the question is from which energy is okay. So by definition, so I'm giving you a definition. The electric potential, okay, so the let's say the electric potential energy, the electric potential, be careful, energy so U of the charge is the opposite of this work. Okay? So, of course, you have guessed that the energy required to move the charge from I to J is coming from the electric field. Okay? So, we can define an electric energy. This electric energy is the energy which can do the work. Okay? Okay? So, the work is coming from the electric potential energy, and by default, this is 6. Okay? Okay. And by definition, this is not, sorry. I'm sorry, it's not this definition. This is the physics, sorry. I'm sorry. The electric potential energy of the charge is such. Sorry. Yes. Okay. So now, by definition, the electric potential. Okay. Now, the electric potential is V equal U over Q. Okay? So this is an energy divided by the charge. Okay, so again, so of course, okay, so again, the energy required to move the charge in the field E is coming from an electric potential energy. It is important, electric potential energy, U, okay? But from this we can define an electric potential, which is the electric potential energy divided by the charge. In such a way, the electric potential is independent of the charge. Okay? Okay. So this is important to not confuse the electric potential, which is different from the electric potential energy. Is that okay for you? Okay. So if, of course, U is the joule, the charge is the coulomb, so the unit of the electric potential is joule by coulomb, and this is by definition volt. Okay? Okay, so now remark the work from E to G equal, so I said, minus, it's not good here. Okay, so is equal minus its Q, the potential at point G minus the potential at point E. Okay? So now, using this formula, you can calculate the work necessary to move the charge Q from E to G. It's equal the charge minus the charge times the electric potential. Is it okay? You have any question? No? Okay. So, okay, so we can say in summary, we can say that the potential, the electric potential is a kind of potential energy divided by a charge, okay? By unit of charge. Is it okay? Okay, so now, I'm sorry, it's okay? No? You want me to let again? Yes? Okay. Can we continue? Yes? Okay. Okay, the next part is I'm going to talk about equipotential surface. Okay, definition. An equipotential surface is an ensemble of adjacent points where the potential, the electric potential, is the same. Okay? Again, an equipotential surface is an ensemble of points where the electric potential is the same, is equal. Okay? So we can make this drawing like this, for example. Okay, so imagine, of course, similarly to the electric field, it's impossible to visualize the electric field, okay? So we can just draw or imagine the electric field with lines, okay? In the same manner, there is no way to visualize the equipotential surface. We just can draw or imagine them, okay? So this is why so here, for example, we have three equipotential surface. Okay. And if I take a point here, the potential of the point M is equal, for example, of the potential of the point B. Okay? But, of course, the potential here, the point B and M, is different if I take the potential here, the point N, and, okay. Okay, so all the points here have the same potential. Okay, and all the points here, for example, E, so the potential of E equals the potential of N, etc. Okay, you understand this? Okay. Okay, so now, if we consider a charge Q somewhere, the charge Q, the energy required to move the charge Q, for example, to P, on the equipotential surface is equal to zero. Okay? Because, as I said before, here, the work required to move a charge from a point E to G is minus Q times the difference of electric potential. So if we consider a charge moving on an equipotential surface, we do not know where is the equipotential surface, but imagine that we can see it. The energy required to move the charge Q on an equipotential surface is zero. Okay? Okay. The charge in other words, a charge Q can move freely on an equipotential surface. This is another way to do it, to say it. Okay, but now just another way. If we can take the charge Q, for example, here, and now we are going to move from another point N, for example. Okay, so let's say like this. Of course, when a charge change or move from one equipotential surface to another one, the energy required is, again, so of course, delta U, for example, from M to M, you got minus okay? This is the energy that you have to provide to move the charge from M to N. Okay? Is it okay? The thing is, important is, you can see that this energy depends only on the potential at point N and the potential at point N. So, in fact, the moving is not depending on the path. Okay? Remark, this energy does not depend on the path between M and N. Okay? Okay, we will see that. Okay, we'll see it. Okay, so yes, we will see. I will see that later, but I can give you a remark. The electric field at a point of an equipotential surface is perpendicular to this surface. We will see that, okay? See below. Okay. Do you have any question? So now let's see some example. Can I turn my page? Not yet. Okay. can we continue? No? I'm sorry, I'm not writing very well. I would like to make an effort. Let's go. For example, so the so here is a point charge, okay, and by symmetry, the equipotential surface, according to you, what are the equipotential surface of this point charge created by the point charge? So this is, of course, spherical surface around the charge. Okay. So by symmetry, the equipotential surface created by a point charge are a family of concentric sphere. It's okay for you? Okay. And of course, you know that, or you already know that the field created by the charge are radial like this. Okay, so this is E, and this is equipotential surface. You understand? Okay, so if you have another example, if I consider a plane of charge okay, so this is, yes, we can. Imagine a plane like this. So, according to you, what are the equipotential surface created by this plane? Exactly. The equipotential surface are plane parallel to the okay? So by symmetry again, so here, equipotential surface. And of course, the electric field are perpendicular to this plane for planar equipotential surface. Okay? Okay, so next part. Now I'm asking you, what is exactly the relationship between the electric field and the electric potential? Okay, so we are going to call this 24.3. Electric field and potential. Okay, so let's consider again a charge Q. Okay, and the charge Q is making a small displacement, okay, in a field an electric field E. Of course, the equipotential surface again are perpendicular. Okay. So equipotential surface. Okay? small displacement. Okay, ds. Do you follow me? Okay. So during this small displacement, the work of the electric field, the force. Okay. Of course, I didn't mention it, but you have already guessed that the charge is submitted to the electric force Fe. Okay. Okay. So for this displacement, the work of the electric force is, so because it's a small displacement, then it will be a small work. It is equal to the dot product F times ds. Right? Is it okay? And as I read this work is also, as I said before, the variation of the electric energy. So it's also equal to the variation of the equipotential, of the potential surface. Okay? So the relationship, of course, I didn't mention, but the force electric is equal to the electric field times Q. Okay, so we can, if we do that on this, so we have E dot ds equal minus dV. So this is the first relationship. Of course, on the macroscopic path, okay, let's say E G on the path EG, you have this relationship. The variation of electric potential is equal to the integral of E from E to G, from I to J, of minus E times ds. Okay? Okay, but another way to write the things it's okay? Can I continue? It's okay? Can I go on? Yes? Okay, so another thing, oh, maybe. Yes. We can also write now that the field is equal to minus dV over ds. Okay? Do you understand? But this is not a good mathematical way. It's not a correct mathematical, not, it's a bad writing. Okay? Why is it a bad writing? Because in math, we do not know what is it to divide a number, dv, by a vector, ds. You understand? Okay? It's not possible to write like this. So, the good writing is do you know the gradient? So this is, in French, it is like this. Gradient. Do you, or maybe in US or in Vietnam, we can write like this. Is that correct? The gradient. This is a mathematical operator. Okay, it's a vector. It's a gradient of v. Okay? So, just to let me specify a little bit, in a Cartesian referential reference, so x, y, z, okay? The potential, so okay, the potential, the electric potential is a property of each point in the space, right? So we can say that the potential is a function of x, y, z, where x, y, z are the coordinates of the point. Are you agree? Yes, do you follow me? Okay, so the definition of the gradient, E equal minus gradient of V is equal, okay, minus, by definition of the fixed, it's the derivative of V over x times ux uz. So the reference is ux, uy, uz. Okay, so this is one way to calculate. Okay. So do you know what is the gradient? Who do not know? Oh, so you all know what is it? Yes? Okay, this is the sign for derivative.
Derivative.
It's like this.
D over dx.
Exactly. Derivative relative to x. Okay? Okay, and this by definition, this show that E is always perpendicular to equipotential. Okay? By definition, the gradient is always perpendicular to the surface. This is the mathematical property. Okay? Okay. So now let's detail a little bit. Can I continue? Okay. So no. Okay, so my question is, see here, in the previous example, I have drawn the equipotential surface. Okay, for example, in the case of point charge, but just by considering the symmetry of the problem, we know that the equipotential surface are spherical surface. But now we would like to know what is the value of the equipotential surface for a distance from the charge. Okay, so we are going to use this. So 24.4. So electric potential created by a point charge okay, so we have a charge Q, we have a point M, and the question is, at this point, what is the potential? Okay? Okay, so we know that the equipotential surface are spherical sphere like this. We know that the electric field is like this. Okay, so to do this, remember, okay, this is the potential the electric potential created by a charge Q. Okay? But to answer the question, we are going to imagine, here for example, let's imagine all the people. Imagine that we are going to bring another charge, big Q, whatever the value, from infinity. Okay? Very far. So we are going to consider a charge Q very far, and we are going to bring it, let's say, to here. Okay? So each time we have a small ds like this. So ds is like this. Okay? Okay, I didn't mention, but here the distance between the origin is r. Okay. Do you understand can you imagine the experiment? Okay, there is my charge Q here. I'm bringing another charge big Q until here. Okay? So, what is the work? Is it necessary to calculate this? No, I think it's not necessary to consider this. Oh yes, we can say. Okay, whatever. It's the same. Okay. So the work to do that again. Yes, I didn't mention that. Okay. So the work again of this process equal minus Q. Okay, so it's equal to the force from infinity to m, okay, of Q E times dx. Okay, because the force, okay, and we also know that it is equal to minus Q, the density, the potential of okay. So the work to do this process is again the integral of the infinity from the infinity to m of the force time the displacement, and we know that this is just minus q, big Q, sorry, big Q, times v of m minus v of infinity. Okay, this is big Q, okay? Okay, so just to tell you that we have this. Of course, we can consider that the potential at the infinity, because it is very, very far from the charge Q, is not influenced by the charge Q, so we can say by reference that it is equal to 0. Yes, question?
No, I want to use paper.
Like this?
Yeah,
Sorry.
I don't have any question.
And again, this equation is only the integration of this one. Okay?
Teacher,
Yes.
can you go again why it's equal to 0?
Your question is why the potential at the infinity is 0?
Yes.
Because if you are very far from charge, the influence of the charge has the charge has no influence of somewhere very far. Okay, so we can decide that the potential at very far is just 0. There is, okay? Okay. So now we know that what is the electric field created by a charge. So we have V of m, which is what it wants to do, is so 1 over 4p epsilon 0, the charge Q over R, okay, times ds. I didn't mention. Oh, sorry, I did mistake, but whatever. Okay, so are you agree with that? Yes? Okay, so now, now the infinity is very far from here, and I said that the potential, the work does not depend. So now let's imagine here that the infinity is here in fact. Okay? So now the ds are like this. You agree with that? Okay, because the infinity has no space. No, it's not a point, in fact. Okay? So, the ds is equal to, what is it? Oh, sorry, there is 2 here. There is 0.2 here. So ds here is equal to minus dr, dr being here. Okay. Okay, so at the end we have the potential. Oh, sorry. I did somewhere. Oh, yes. Sorry. Here, the point, the vector u is equal. There is a dot product. Okay. The dot u is here. So at the end, we have this. No, sorry. No. Did I make a mistake somewhere? -0. This is minus. Oh, no. Yeah, okay. So this is equal, so you can integrate this. So the integration of 1 over R2 is minus, okay, Q over 4P epsilon 0 R. I don't understand why I have a minus sign. Could you help me? I don't understand why I have a minus sign. Maybe it's here. It's not minus. I did a mistake somewhere. Did you see the mistake? I did an error somewhere. the conclusion is that a potential created by a point charge is this. Okay? Okay, what time is it?
12 o'clock.
At what time do we have to finish?
Till 10.
10?
Yeah.
Okay, we have 10 minutes to do the last thing. Okay, sorry. So 18. So now, okay, this is the potential created by a point charge. Now the question is, what is the potential created by a dipole? Okay. Okay. So again, we have two charge at point P and okay. Here we have a minus q, we have a plus q, and the distance here is d. Okay, this is a dipole. Can you follow me?
Yes.
Yes? Okay. So, and now the question is, from this, again, at the point M, what is the potential at this point? Okay? So, now we have calculated the potential of one created by one charge. So it's easy to calculate the potential of the dipole. It is the potential created by the charge positive plus the potential created by the negative charge. Okay? Okay, so now we can do this. So this is equal to 1 over 4p epsilon 0 q. So the distance between the potential is 1 over the distance pm and 1 over the distance nm. Okay? It's okay with you? Okay. So, of course, this is the distance nm minus the distance pm over the product of the two. Okay. So we need to calculate this distance, okay? But I am going to make an assumption. In the approximation, so OM, okay, it's much more higher or larger than PM and NM. Okay? We are going to do this. So that means in this assumption, please quiet, 10 minutes. So in this assumption, it is like it is almost like the line from PM to NM are parallel. You see that? Okay, so now I can introduce what is the distance R. So R is the distance between O and M, and theta, I am going to introduce this. Theta is the angle between the unit vector from the negative charge to the positive charge, so U and OM, okay? So in that direction, in this approximation, so NM minus PM, you can see that it's like this. You have here, this distance here is NM minus PM. Are you agree with that? Yes? Okay, so this distance is equal to, so this is D, of course. So this distance is equal to D cos theta. Okay, so in this distance, in this approximation, NM minus PM equal D cos theta, and of course PM times NM equal R2. Okay? So at the end, the potential at the point M created by the dipole is equal to Q D cos theta divided by 4 P epsilon 0 R2. Okay? But we can also, if we introduce the moment, the dipole moment, do you remember? What is the dipole moment P? Okay, it's equal to Q D times the unit vector. Okay, so that means that Q D cos theta equal the dot product between the vector P and U. Is that, no, sorry, not vector, between the vector, R, but we need to divide it by R. Okay, so finally, we can write that F3 Okay, I would like just to finish one thing. Just to mention, I won't do any demonstration, but I would like to show you the electric potential created by a charged conductor. Okay, so, and let's say a spherical conductor. So, okay, this is a spherical conductor. And of course, in a spherical conductor, as I show you, the charge are located at the surface of the conductor. You remember? Do you remember? Okay? And so the question is, what is the electric potential and the potential, yes, at this point. So for the electric potential, we already know, okay, so it is like this. So of course, sorry, the spherical conductor has radius r, okay. So what is the value, the magnitude of the electric field E as a function of r, which is the distance between the center of the sphere and the point M? Okay, so this is you can show it, but as I said before, inside the spherical conductor, it's equal, the electric field is equal to, what did I say? 0. Thank you. Okay, 0. And then outside, you know, if you apply the Gauss law, you will find the electric potential is the electric potential created by a point charge. So it's like this. Okay? This is function. And now, because the electric field inside the conductor equal to 0, that means that the potential inside is equal to the potential at the surface of the conductor, right? So the potential should be something like this. And then after that, the potential created by the spherical conductor, you can apply it. It's only like this. This is because it's the derivative of this. Okay? So this is the value of the potential, of the electric field, and this is the value of the potential electric. It's okay? Do you have any question? No? Okay, so I have finished the course for today. Thank you for your attention.